Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. What happens at the edge of a black hole? At the edge of a black hole lies one of the most extreme boundaries in the universe, a point of no return called the event horizon. This invisible surface marks the place where gravity becomes so overwhelmingly powerful that nothing, not even light itself, can escape. Cross this threshold, and you are severed from the rest of the universe forever, drawn inexorably toward the singularity at the center. Understanding what happens at this edge requires thinking about space and time in ways that challenge everything. Our everyday experience tells us about how reality works. Imagine approaching a black hole from a safe distance. At first, it wouldn't look like much, just a region of absolute darkness against the star-filled background of space. But as you drew closer, you would begin to notice something strange happening to the light around you. Stars behind the black hole would appear distorted, their light bent around the black hole's mass in graceful arcs. Some stars would appear in multiple locations simultaneously as their light took different curved paths around the black hole to reach your eyes. This gravitational lensing creates a visual effect like looking through a cosmic funhouse mirror, with the entire background of space warped and twisted around the dark sphere. The event horizon itself is defined by a specific radius from the center of the black hole, called the Schwarzschild radius. For a black hole with the mass of our Sun, this radius would be about 3 kilometers. For a supermassive black hole, like the one at the center of our galaxy, which contains about 4 million times the Sun's mass, the event horizon stretches millions of kilometers across. The radius grows linearly, with mass double the mass and you double the radius. Despite these varying sizes, the fundamental nature of the event horizon remains the same. It's the mathematical surface where the escape velocity equals the speed of light. Think about what escape velocity means. On Earth, you need to throw something upward at about 25,000 miles per hour for it to escape the planet's gravity and never fall back down. Get closer to a massive object and the escape velocity increases. At the event horizon of a black hole, the escape velocity reaches 186,282 miles per second. The speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever escape. But here's where things become truly strange. Time itself behaves differently near a black hole's edge. According to Einstein's general relativity, gravity doesn't just bend space, it warps time as well. The stronger the gravity, the slower time passes relative to an observer far away from the gravitational source. Near the event horizon, this time dilation becomes extreme. Picture two observers, one hovering safely far from the black hole, another descending toward the event horizon. The descending observer checks their watch, and everything seems normal to them. Time passes at its usual rate from their perspective. They breathe normally, their heart beats regularly, they think their thoughts at the normal pace. But to the distant observer watching through a powerful telescope, something bizarre is happening. The descending person appears to be moving slower and slower. Their movements become sluggish. Their signals take longer and longer to arrive, and as they approach the event horizon, they appear to nearly freeze in place. This isn't an optical illusion or a trick of perception. Time genuinely runs slower in stronger gravitational fields. As the descending observer approaches the event horizon, each second they experience corresponds to longer and longer periods for the distant observer. At the exact moment they cross the event horizon, from the distant observer's perspective, time for them appears to stop completely. They would appear frozen at the edge, never quite crossing over, their image becoming increasingly redshifted and dim, eventually fading from view entirely. But from the perspective of the person crossing the event horizon, nothing special happens at that precise moment. There's no wall, no barrier, no sensation of crossing a threshold. They would pass through the event horizon and continue falling inward, still experiencing time normally from their own reference frame. This is one of the most counterintuitive aspects of black holes. The event horizon is only special to outside observers. To someone crossing it, the moment passes without any local indication that anything significant has occurred. However, there is something that would become increasingly noticeable as you approached and crossed the event horizon: tidal forces. These arise because gravity weakens with distance, and different parts of your body would be at different distances from the black hole's center. If you fell feet first toward the black hole, your feet would experience stronger gravity than your head. This difference in gravitational pull creates a stretching force. For a stellar mass black hole, these tidal forces become extreme well before you reach the event horizon. The difference in gravitational pull between your head and feet would stretch you vertically while simultaneously squeezing you horizontally, a process astrophysicists have termed spaghettification. Long before reaching the event horizon, the tidal forces would overcome the molecular bonds holding your body together, stretching you into a thin stream of atoms. This would be an absolutely fatal experience occurring far from the event horizon itself. For supermassive black holes, the situation is different. Because they're so much larger, the tidal forces at the event horizon are actually quite mild. You could cross the event horizon of a supermassive black hole, and for a while at least, experience no unusual forces at all. The spaghettification would come later, as you continued falling inward toward the singularity where tidal forces eventually become infinite, regardless of the black hole's size. The event horizon is also where the nature of space and time exchange roles, in a sense. Outside the event horizon, you can choose your direction in space. You can go left or right, up or down, toward or away from the black hole. Time, on the other hand, only flows in one direction, forward. But once you cross the event horizon, this changes. Moving inward toward the singularity becomes as inevitable as moving forward in time is outside the black hole. Just as you can't choose to move backward in time in normal space, you can't choose to move away from the singularity once inside the event horizon. All possible paths through space-time, every trajectory you could take, lead inward. Light behaves strangely at the event horizon as well. Just outside the horizon exists a region called the photon sphere, where light can orbit the black hole in unstable circular paths. Photons at exactly this radius, moving in exactly the right direction, will circle the black hole indefinitely, though any tiny perturbation will cause them to either spiral inward or escape outward. If you could somehow position yourself at the photon sphere and look sideways, you might theoretically see the back of your own head as light from you travelled around the black hole and returned. At the event horizon itself, photons can move along the surface, neither escaping nor falling inward, but this is an unstable equilibrium. Any photon aimed even slightly inward will fall toward the singularity. Any photon aimed even fractionally outward will escape to infinity, though heavily redshifted by the time it reaches distant observers. The effects of gravitational redshift become extreme near the event horizon. Light climbing out of a deep gravitational well loses energy, shifting toward longer wavelengths, toward the red end of the spectrum and beyond into infrared and radio waves. A flashlight shining from near the event horizon would appear dimmer and redder to a distant observer. Right at the event horizon, light is redshifted infinitely, meaning the energy of any photon trying to escape becomes zero. This is another way of understanding why nothing can escape. Even light, trying to leave the event horizon, has all its energy drained away by the gravitational field, Black holes can rotate, and rotation adds another layer of complexity to the event horizon. A rotating black hole drags space-time around with it in a process called frame dragging. Close to the black hole, space itself is being pulled around in the direction of rotation. There's a region called the ergosphere outside the event horizon, where this frame dragging is so strong that nothing can remain stationary. Everything must rotate with the black hole, even if it has enough energy to eventually escape. For a rotating black hole, the event horizon is actually smaller than it would be for a non-rotating black hole of the same mass, and it's oblate rather than perfectly spherical, bulging slightly at the equator. At the poles, you could get closer to the singularity before crossing the point of no return than you could at the equator. The material falling into a black hole doesn't simply disappear the moment it crosses the event horizon. Before crossing, matter often forms an accretion disk, a swirling disk of gas, dust, and plasma spiraling inward. Friction in this disk heats the material to tremendous temperatures, often millions of degrees, causing it to radiate intense X-rays and other radiation. This radiation comes from outside the event horizon and can escape, making accreting black holes among the brightest objects in the universe, even though the black hole itself emits nothing. As material in the accretion disk spirals closer to the event horizon, it accelerates to tremendous velocities, often reaching significant fractions of the speed of light. The innermost stable circular orbit, the closest distance where material can orbit without inevitably falling in, lies just outside the event horizon. Material at this radius whips around the black hole in fractions of a second, subjected to intense tidal forces and heated to extreme temperatures before making its final plunge across the event horizon. At the quantum level, something remarkable happens right at the event horizon. Stephen Hawking predicted that quantum effects near the event horizon would cause black holes to emit radiation, now called Hawking radiation. Virtual particle pairs constantly pop into existence throughout space, normally annihilating each other almost immediately. But at the event horizon, one particle of the pair can fall into the black hole, while the other escapes. To a distant observer, the black hole appears to be emitting radiation with a temperature inversely proportional to its mass. For stellar mass black holes, this temperature is incredibly tiny, far colder than the cosmic microwave background, so the effect is purely theoretical at present. But over unimaginably long timescales, Hawking radiation would cause black holes to slowly evaporate. The event horizon represents one of the most profound boundaries in physics, a one-way membrane in space-time itself. It's a place where our intuitions about time, space, and causality break down, where the fabric of reality becomes so warped that the normal rules no longer apply. Everything that crosses this boundary is lost to the outside universe forever, adding to the black hole's mass and slightly expanding its event horizon, while the information about what fell in appears to be lost forever, creating paradoxes that physicists still struggle to resolve. The edge of a black hole is truly an edge, not just of a physical object, but of our ability to observe, to know, and to understand the universe. Why nothing can go faster than light? Light moves at exactly 300,000 kilometers per second in a vacuum, fast enough to circle Earth more than 7 times in a single second. This speed seems arbitrary at first, just another number to memorize. But the speed of light represents something far more profound than a mere velocity. It's a fundamental limit built into the structure of the universe itself, a cosmic speed limit that nothing with mass can reach, let alone exceed. Understanding why nothing can go faster than light means understanding one of the most revolutionary insights in physics, that space and time are not separate, unchanging backdrops to events, but are woven together into a unified fabric that behaves in deeply counterintuitive ways. Before Albert Einstein published his special theory of relativity in 1905, most physicists assumed that velocities simply added together in straightforward ways. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, then someone standing beside the tracks would see the ball moving at 70 kilometers per hour. This common sense addition of velocities works perfectly well at everyday speeds. But Einstein realized that this intuitive picture breaks down at velocities approaching the speed of light, and the breakdown reveals something fundamental about the nature of space and time. Einstein started with two basic principles. First, the laws of physics should be the same for everyone moving at constant velocity, regardless of how fast they're going. This principle of relativity had been around since Galileo, and it accords with common experience. You can't tell from experiments done inside a smoothly moving train whether the train is moving or the station is moving past you. Second, and more radically, Einstein proposed that the speed of light is the same for everyone, regardless of how fast they're moving or how fast the light source is moving. This second principle contradicts our everyday intuition about velocity addition. If you're on a train moving forward and you shine a flashlight forward, you might expect someone on the platform to measure the light going faster than someone on the train would measure it, by an amount equal to the train's speed. But experiments repeatedly showed that this doesn't happen. The person on the platform and the person on the train both measure exactly the same speed for the light. This bizarre result seems impossible if we assume that space and time are absolute and unchanging. Einstein's breakthrough was realizing that space and time must not be absolute. Instead, they must adjust themselves to keep the speed of light constant for all observers. When you move faster, time actually slows down for you relative to someone standing still, and distances contract in your direction of motion. These effects, called time dilation and length contraction, are not optical illusions or measurement errors. They're real physical changes in how time flows and how space extends. At everyday speeds, these relativistic effects are incredibly tiny, too small to notice. A person traveling in a car at highway speed experiences time flowing more slowly than someone standing still, but the difference amounts to only billionths of a second over a lifetime. But as speeds approach the speed of light, these effects become dramatic. At 90% of light speed, time runs at only about 44% of the normal rate. At 99% of light speed, time runs at about 14% of normal. As you get closer and closer to light speed, time slows down more and more dramatically, approaching a complete stop as velocity approaches the speed of light. This time, dilation has been confirmed through countless experiments. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground, by exactly the amount Einstein's equations predict. Particles called muons, created when cosmic rays strike the upper atmosphere, live for only about 2 microseconds before decaying. At the speeds they travel, close to the speed of light, time dilation extends their lifetimes enough that they reach the ground before decaying, something that would be impossible if time flowed normally for them. GPS satellites must account for relativistic time dilation, both from their speed and from Earth's gravity, or they would accumulate errors of several kilometers per day. Length contraction is equally real. A spaceship traveling at 99% of light speed would be compressed to about 14% of its rest length in the direction of motion from the perspective of someone watching it pass by. From the crew's perspective, inside the ship, they wouldn't feel compressed. They would measure their ship as having its normal length, but they would measure the distance to their destination as being contracted, appearing much shorter than it does to someone at rest relative to the destination. These strange effects arise from the fact that the speed of light must be the same for everyone. If you're chasing a beam of light at 99% of light speed, you still measure that light beam as moving away from you at full light speed, not at 1% of light speed as you might expect. This only makes sense if time is flowing more slowly for you, and distances are contracted in your reference frame. The adjustments exactly compensate to keep the speed of light constant. But what happens if you try to accelerate something to light speed? Here's where the cosmic speed limit becomes absolute. As an object with mass accelerates, it gains kinetic energy. In classical physics, kinetic energy depends on velocity in a simple way. Double the velocity, and kinetic energy increases by a factor of 4. But Einstein showed that the relationship changes as you approach light speed. The energy required to accelerate an object increases more and more dramatically as velocity increases, and as you approach light speed, the energy required approaches infinity. This happens because of something called relativistic mass increase. As an object moves faster, it becomes harder to accelerate. It behaves as if it's getting more massive. At 90% of light speed, an object has about twice its rest mass. At 99%, it has about 7 times its rest mass. As velocity approaches light speed, the relativistic mass approaches infinity. To actually reach light speed would require infinite energy to accelerate infinite mass, a physical impossibility. Light itself travels at light speed because photons, the particles of light, have no mass. Maxwell's equations, which describe how electromagnetic fields behave, predict that electromagnetic waves travel at a specific speed determined by properties of space itself. Einstein realized that this speed is the cosmic speed limit, and that massless particles must travel at exactly this speed. Photons don't have to accelerate to light speed. They're created already moving at light speed, and they can never slow down or stop as long as they exist. Other massless particles like gluons, which carry the strong nuclear force, also travel at light speed. Gravitational waves, ripples in space-time itself, travel at light speed as well. Mass is what prevents particles from reaching this ultimate speed. Any particle with mass can approach light speed arbitrarily closely if given enough energy, but can never quite reach it. The relationship between energy, mass, and velocity is captured in Einstein's famous equation, E=mc², though this is actually a special case of a more general equation. The full equation shows that total energy equals the rest mass energy plus kinetic energy, and as velocity increases, more and more of the total energy goes into the kinetic energy component. At very high velocities, most of the energy is kinetic rather than rest mass. Particle accelerators demonstrate these principles directly. The Large Hadron Collider accelerates protons to more than 99.99% of light speed. At these velocities, the protons have about 7,000 times more energy than their rest mass energy. Accelerating them to even higher velocities, getting closer to light speed, requires exponentially more energy for each incremental increase in velocity. No matter how much energy you put in, the protons never quite reach light speed, and the energy required to actually reach it would be infinite. Some people wonder whether traveling faster than light might be possible by warping space rather than moving through it. General relativity does allow for exotic spacetime geometries, like wormholes or warp drives, that could theoretically allow effective faster-than-light travel without actually moving through space faster than light. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical way to contract space in front of a spacecraft and expand it behind, allowing the spacecraft to effectively travel faster than light while locally moving slower than light relative to the space immediately around it. However, these solutions require exotic matter with negative mass or negative energy density, properties never observed and possibly forbidden by quantum mechanics. Even if such matter could exist, the energy requirements would be astronomical, potentially requiring more energy than exists in the entire observable universe. These remain purely theoretical concepts, with no practical pathway to implementation, and they don't violate the fundamental principle that nothing can move through space faster than light. The cosmic speed limit has profound implications for space travel. Even at light speed, it would take over 4 years to reach the nearest star beyond our Sun, Proxima Centauri. Travelling to the centre of our galaxy would take over 25,000 years at light speed. Reaching nearby galaxies would take millions of years. The vast distances between stars and galaxies, combined with the absolute speed limit, mean that interstellar travel remains extraordinarily challenging even in principle. For travellers moving at near-light speeds, time dilation provides a partial solution. From the crew's perspective, a journey might take only months or years, while decades or centuries pass on Earth. This time dilation allows relativistic travellers to cross vast distances within their own lifetimes, though everyone they knew would age far more or be long dead by the time they returned. This creates a fundamental asymmetry. The traveller's time and the stay-at-home's time flow at different rates, and there's no way to make them match up again. The speed of light also limits how quickly information can travel. When you see a star in the night sky, you're seeing it as it was years or centuries ago. That's how long the light took to reach you. The sun you see is 8 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8 minutes. This light travel time creates what physicists call a light cone, the boundary between events that can influence you and events that cannot because they're too far away in space and too close in time for light to have travelled from there to here. Causality itself depends on the cosmic speed limit. If information could travel faster than light, it would be possible to send messages backward in time, to communicate with your own past. This creates logical paradoxes, like sending a message to your past self, telling yourself not to send the message. The speed of light limit prevents these paradoxes by ensuring that cause always precedes effect for all observers, regardless of their motion. The universe seems designed in a sense with this speed limit built in. Light speed isn't just the speed at which light happens to travel, it's a fundamental property of space-time itself, woven into the structure of reality. Mass is what prevents particles from reaching this ultimate speed, and the closer you get to it, the more energy is required to go faster, asymptotically approaching infinite energy at the limit. This speed limit connects space and time in an intimate way. Space and time aren't separate entities but are aspects of a unified, four-dimensional space-time. Events that appear simultaneous to one observer might not be simultaneous to another observer moving differently. The cosmic speed limit defines the structure of this space-time, determining how space and time mix together as observers change velocity. Why nothing can go faster than light ultimately comes down to the structure of space-time itself. The speed of light isn't a speed limit in the sense of a rule imposed from outside. It's a fundamental property of how the universe is built, how space and time relate to each other, and how energy and mass behave. Reaching light speed would require infinite energy. The only things that can travel at light speed are things with no mass, like photons, which must always travel at this speed. Everything else, everything with mass, can only approach this ultimate velocity, forever accelerating, but never quite reaching the cosmic speed limit that defines the maximum rate at which anything can travel through the fabric of space-time. Why alien life might be microscopic. When we imagine alien life, our minds often conjure images of intelligent beings piloting spacecraft, complex organisms with eyes and limbs exploring alien landscapes, or at minimum, creatures we could observe and recognize as alive. But this expectation might be profoundly misguided. Earth's history offers a sobering perspective. For roughly 3 billion of the 4 billion years that life has existed on our planet, all organisms were microscopic. Bacteria, archaea, and single-celled eukaryotes dominated Earth's biosphere for the vast majority of life's history. Complex multicellular organisms, plants, animals, fungi, are recent arrivals, having existed for less than 1 billion years. If Earth's timeline is any indication, most life in the universe might be microscopic, existing as single cells or simple colonies that never evolve into the complex macroscopic forms we're accustomed to seeing. The transition from single-celled to multicellular life represents one of the most difficult evolutionary innovations in Earth's history. It only happened once in the bacterial lineage, never successfully transitioning beyond simple filaments and colonies, and only a few times in the eukaryotic lineage, producing plants, animals, and fungi. This rarity suggests that while single-celled life might emerge relatively easily wherever conditions permit, the evolution of complex multicellularity requires specific circumstances that might not commonly occur. Many alien worlds might develop thriving microbial biospheres that remain forever microscopic because the evolutionary innovations needed for large, complex organisms never occur. Energy availability represents the first major constraint on complexity. Complex multicellular organisms require substantial energy to build and maintain their bodies. They need energy to power specialized organs, to move through their environments, to grow to large sizes. Most of this energy ultimately comes from oxygen-based metabolism, which releases far more energy per molecule of food than anaerobic metabolism does. The efficiency of oxygen metabolism, about 15 times more energetic than the best anaerobic alternatives, enabled the evolution of large active organisms on Earth. But oxygen was not always available in Earth's atmosphere. For the first 2 billion years or more of life's existence, the atmosphere contained very little free oxygen. Life during this time remained entirely microscopic and relatively simple, constrained by the low energy yields of anaerobic metabolism. Only after photosynthetic bacteria evolved and began producing oxygen as a waste product did atmospheric oxygen accumulate, and only after oxygen reached substantial levels could organisms evolve the high-energy metabolisms necessary for large size and complexity. Many alien worlds might never undergo this transition. If photosynthetic life never evolves, or if it evolves but produces different waste products, perhaps using electron donors other than water that don't release oxygen, the atmosphere might remain oxygen poor indefinitely. Life on such worlds would be permanently restricted to anaerobic metabolism, with its inherent energy limitations preventing the evolution of large complex organisms. The biosphere might flourish with countless microscopic species filling every available niche, but nothing larger than perhaps a millimeter would ever evolve, because the energy budgets of anaerobic metabolism cannot support larger sizes or more complex structures. Predation drives much of the evolution toward complexity on Earth. The development of predators created selection pressure for prey to evolve defenses, armor, toxins, multicellularity that makes them too large to be consumed by single-celled predators. Predators, in turn, evolved mechanisms to overcome these defenses: better sensing systems, faster movement, cooperative hunting. This evolutionary arms race between predators and prey drove increasing complexity, with both sides becoming more sophisticated over generations. The transition to multicellularity in animals might have been driven at least partially by predation pressure from other single-celled organisms. On an alien world where predation never becomes significant, perhaps because environmental conditions don't favor the evolution of heterotrophs, or because chemical energy is so abundant that organisms don't need to consume each other, this driver of complexity would be absent. Life might remain a collection of bacteria-like organisms metabolizing chemicals from their environment, with no selection pressure favoring the evolution of larger, more complex forms. Without predation or competition driving an evolutionary arms race, the biosphere might reach an equilibrium of simple, efficient microorganisms that persist unchanged for billions of years. The evolution of eukaryotic cells with nuclei and complex internal structures, required an extraordinarily unlikely event called endosymbiosis, where one cell engulfed another and instead of digesting it, established a permanent symbiotic relationship. On Earth, mitochondria, the energy-producing organelles in eukaryotic cells, originated as free-living bacteria that were engulfed by other cells and eventually became integrated parts of those cells. This event, which happened roughly 2 billion years ago, was apparently unique in Earth's history. It happened once, and all eukaryotic cells descend from that single event. Eukaryotic cells made complex multicellular life possible. Their mitochondria provide far more energy per cell than bacteria can generate, allowing cells to support larger genomes and more complex structures. Their internal compartmentalization allows specialized biochemistry to occur in different cellular regions. Their complex cytoskeletons enable intricate cell shapes and coordinated movements. Without eukaryotic cells, complex multicellular organisms probably could not evolve. If endosymbiosis was difficult, requiring very specific circumstances to occur even once on Earth, alien worlds might never undergo this transition. Life might remain forever bacterial, lacking the cellular complexity necessary as a foundation for multicellular organisms. These worlds would have rich microbial ecosystems with tremendous diversity at the microscopic level, but would never produce organisms visible to the naked eye. Environmental stability influences evolutionary innovation. Earth's environment has been highly variable over geological time. Ice ages, warming periods, asteroid impacts, volcanic catastrophes, changing atmospheric composition, continents drifting and colliding. These environmental changes created selection pressures that favored adaptability and innovation. Mass extinctions wiped out dominant groups, allowing new forms to radiate and diversify. Without such disruptions, dominant organisms might remain unchanged indefinitely, never facing circumstances that favor more complex alternatives. An alien world with a remarkably stable climate and environment over billions of years might never see complex life evolve. Early microbial ecosystems might reach an equilibrium where existing organisms are so well adapted to unchanging conditions that no complex innovations provided advantages. Microbes would efficiently fill every niche, processing every available chemical, extracting every erg of available energy, and no evolutionary pressure would favor the metabolically expensive transition to larger, more complex forms. The planet would remain microbial forever, not because complex life is impossible, but because stable conditions never create circumstances where complexity is advantageous. The availability of ecological niches affects diversification. On Earth, new environmental niches continuously opened as continents drifted, climates changed, and oxygen accumulated in the atmosphere. Moving onto land created entirely new sets of niches, terrestrial environments with different challenges than aquatic ones. Flying created another set of niches. Each new opportunity drove adaptive radiations where organisms evolved to exploit newly available resources and habitats. A planet lacking this niche diversity might not provide opportunities for complex life to evolve. A world completely covered by ocean with no land would lack terrestrial niches. A world with a homogeneous environment, perhaps a global ocean with uniform temperature and chemistry from pole to pole, would offer fewer distinct niches than Earth's highly varied environments. With fewer niches available, there would be less opportunity for adaptive radiation and less selection pressure driving organisms toward the specializations and complexities that fill diverse ecological roles. Timescales matter significantly. Evolution proceeds through random mutations and natural selection, accumulating beneficial changes over countless generations. Complex innovations require many individual evolutionary steps, each one building on previous changes. The evolution of eyes, for instance, required the initial evolution of light-sensitive proteins, then the gathering of these proteins into light-sensitive patches, then the invagination of these patches into cups that provide directional information, then the development of lenses that focus light, then the neural processing systems to interpret visual information. Each step took many generations and many mutations. On an alien world where organisms have very long generation times, perhaps living for thousands of years before reproducing, evolution would proceed extraordinarily slowly. A complex innovation that might evolve in tens of millions of years on Earth, where many organisms reproduce annually or even faster, might take billions of years on a world where generation times are measured in millennia. If the planet star has a relatively short lifetime, perhaps a massive star that will exhaust its fuel in a few billion years, there might simply not be enough time for complex life to evolve before the star's death sterilizes the planet. The chemical environment limits biological complexity. Complex organisms require diverse biochemistry, proteins for structure and catalysis, lipids for membranes, nucleic acids for information storage, carbohydrates for energy and structure. Building these diverse molecules requires access to various elements in appropriate forms. A planet poor in essential elements, perhaps lacking sufficient phosphorus, nitrogen, sulfur, or trace metals, might not provide the chemical building blocks necessary for complex biochemistry. Life might arise using simpler chemistry, but might be unable to evolve the molecular diversity needed for complex cells and multicellular structures. Physical constraints on size affect what complexity is possible. Surface tension becomes increasingly important at small scales. For microscopic organisms living in water, surface tension is a significant force. Water behaves more like thick syrup than like the thin fluid humans experience. Moving through water at microscopic scales requires different strategies than swimming at macroscopic scales. These physical differences mean that microorganisms experience a fundamentally different physical world than large organisms, and the adaptations that work well at microscopic scales might not scale up successfully. The speed of light sets absolute limits on how quickly information can be transmitted within an organism. For microscopic cells, this is never a constraint. Signals cross the cell in negligible time. But as organisms grow larger, signal transmission times become significant. A 1-meter organism experiences light travel times of about 3 nanoseconds, still essentially instantaneous for chemical and neural signals. But organisms must coordinate their parts, and this coordination becomes more difficult as size increases. Neural signals in humans travel at speeds of about 100 meters per second, meaning signals take milliseconds to travel from extremities to brain. For a hypothetical organism many meters or kilometers in size, coordination would become increasingly difficult. Detection bias affects our perception of what life looks like. Humans evolved to perceive objects roughly our own size. We see animals, plants, and landscape features easily because our sensory systems are optimized for that scale. Microscopic organisms are invisible without technological assistance. An alien observer visiting Earth equipped with sensing systems similar to human vision might conclude that Earth has relatively little life, missing entirely the vast microbial world that actually dominates in terms of biomass, diversity, and metabolic activity. Similarly, when we search for alien life, our methods tend to focus on detecting macroscopic effects, oxygen in atmospheres produced by photosynthetic organisms, changes in planetary albedo from vegetation, perhaps even artificial lights from technological civilizations. A planet covered in microbial life, producing no oxygen, with no multicellular organisms, with nothing visible at planetary scales, might appear lifeless to our telescopes, even if it hosts an incredibly rich and diverse microbial biosphere. Statistical considerations based on Earth's history suggest that if we discovered alien life, it would most likely be microscopic. Life existed on Earth for about 3 billion years before complex multicellular organisms evolved. If we randomly selected a moment in Earth's history, there would be a roughly 75% chance of finding only microscopic life. Assuming Earth's timeline is typical, which may or may not be true, most inhabited planets at any given time would be in their microbial phase, with complex life being relatively rare. Why alien life might be microscopic comes down to microbial life being easy to achieve relative to complex life, requiring only basic metabolism, reproduction, and evolution, while complex life requires numerous specific evolutionary innovations, oxygenic photosynthesis or equivalent high-energy metabolism, eukaryotic cells with their mitochondrial endosymbionts, multicellularity with coordinated cells working together, specialized tissues and organs, each one potentially rare or slow to evolve. Many worlds might develop thriving microbial ecosystems within their first billion years, but might never progress beyond that stage, remaining forever inhabited by bacteria-like organisms invisible to the naked eye, yet representing the most common form of life in the universe. A cosmos filled not with civilizations or even visible organisms, but with countless worlds hosting microbial biospheres that flourish in every conceivable environment, from sunlit surface waters to deep subsurface rocks, from hydrothermal vents to subsurface oceans beneath ice. Each microscopic cell representing a success story of evolution in its own right, reminding us that complexity and large size are not prerequisites for biological success, and that if we ever detect life beyond Earth, we should not be disappointed if it consists of nothing more than microbes, because microbial life might be life's most common, most successful, most enduring form across the vast expanse of the living universe. What's left after a star explodes? When a massive star reaches the end of its life and explodes in a supernova, the detonation is one of the most violent events in the universe, releasing in a few seconds as much energy as the sun will radiate over its entire 10 billion year lifetime. The outer layers of the star are blasted into space at thousands of kilometers per second, creating an expanding shell of hot gas enriched with newly forged elements. But the explosion doesn't simply obliterate the star. At the center of the expanding debris, something remains. A compact, incredibly dense object created from the collapsed core. What gets left behind depends on the mass of that core and determines whether the remnant becomes a neutron star, a pulsar, a magnetar, a black hole, or in rare cases, nothing at all. The immediate aftermath of a core collapse supernova leaves behind a proto-neutron star, an extremely hot, dense ball of neutrons about 20 to 30 kilometers in diameter, containing between 1.4 and about 3 solar masses compressed into a volume smaller than a city. The temperature at birth exceeds 100 billion degrees Celsius, making it one of the hottest objects in the universe. Over the next 10 to 20 seconds, the proto-neutron star cools by emitting enormous numbers of neutrinos, ghostly particles that barely interact with matter but carry away 99% of the supernova's energy. As the proto-neutron star cools and stabilizes over minutes to days, it becomes a neutron star, a stellar remnant held up against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons being compressed too closely together. The density is extraordinary, about 500 million tons per cubic centimetre, comparable to compressing all of humanity into a volume the size of a sugar cube. A neutron star is essentially a single gigantic atomic nucleus, held together by gravity rather than the strong nuclear force. The structure of a neutron star is layered and complex. At the surface lies a thin atmosphere, only centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, about a kilometer thick, where matter exists as a crystalline lattice of atomic nuclei, extremely neutron-rich nuclei unlike any found on Earth, embedded in a sea of electrons. These nuclei become increasingly neutron-rich with depth, containing far more neutrons than protons. Deeper still, at the interface between outer and inner crust, neutrons begin to drip out of nuclei, creating a neutron superfluid that coexists with the nuclear lattice. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever, a quantum mechanical phenomenon that can only occur at extremely low temperatures or extremely high densities. In neutron stars, despite the enormous temperatures by human standards, the density is so extreme that superfluidity occurs. The inner crust, extending to about 10 kilometers depth, consists of increasingly exotic arrangements of nuclei and superfluid neutrons. Computer simulations predict that nuclei might arrange into cylindrical rods, flat plates, or even more complex three-dimensional structures, nicknamed nuclear pasta, because of their resemblance to spaghetti, lasagna, and other pasta shapes. This nuclear pasta might be the strongest material in the universe, billions of times stronger than steel. Below the crust lies the outer core, where nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain electrical neutrality. Both the neutrons and protons exist in superfluid and superconducting states respectively. The protons form a superconductor, where electrical currents can flow without resistance. This region makes up the bulk of the neutron star's mass and extends to perhaps 10 to 12 kilometers from the center. At the very center, in the inner core, where densities exceed that of atomic nuclei by factors of 2 to 10, matter might exist in states never observed in laboratories. Neutrons themselves might break down into their constituent quarks, creating quark matter or strange quark matter. Other exotic particles predicted by quantum chromodynamics, the theory describing the strong nuclear force, might appear, including hyperons, kaons, or pion condensates. The exact nature of matter at these densities remains one of the great unsolved problems in physics, accessible only through observations of neutron stars and theoretical calculations. Many neutron stars are born rotating rapidly, spinning tens or hundreds of times per second, inheriting and concentrating the angular momentum of the massive star's core as it collapsed. If the neutron star's magnetic field is tilted relative to its rotation axis, which is common, the neutron star becomes a pulsar. The magnetic field, enormously compressed and amplified during the collapse, can reach strengths of 1 trillion times. Earth's magnetic field. Charged particles accelerated along magnetic field lines near the poles emit beams of radiation that sweep through space like a cosmic lighthouse. When one of these beams sweeps across Earth, we detect a pulse, hence the name pulsar. The pulses arrive with extraordinary regularity. The Crab pulsar, formed in the supernova observed in 1054 AD, rotates 30 times per second. The fastest pulsar known, PSRJ 1748-2446 AD, discovered in 2006, rotates 716 times per second, so fast that its equator is moving at about 24% of the speed of light. At these rotation rates, the neutron star bulges significantly at its equator but holds together through its tremendous gravitational binding and the strength of neutron-degenerate matter. Pulsars gradually slow down over millions of years as their magnetic fields radiate energy and carry away angular momentum. The rate of slowdown reveals the pulsar's age and magnetic field strength. Young pulsars like the Crab slow down noticeably over human timescales. The Crab's rotation period increases by about 38 nanoseconds per day. Old pulsars slow down much more gradually and eventually become too slow to generate detectable pulses, though the neutron star continues existing as a dark, cooling ember. Some neutron stars are born with even stronger magnetic fields, up to 1,000 times more intense than typical pulsars, reaching magnetic field strengths of 10 to the 15th Gauss. These objects are called magnetars, and they're the strongest magnets in the universe. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms become elongated into needle-like shapes. The magnetic field stores so much energy that magnetars occasionally undergo starquakes, sudden rearrangements of the neutron star's crust that release tremendous bursts of X-rays and gamma rays. The magnetar SGR 1806-20 released a giant flare in 2004 that briefly saturated instruments across the solar system, despite being 50,000 light-years away. Not all neutron stars become pulsars. If the magnetic field happens to be nearly aligned with the rotation axis, the beams don't sweep across our line of sight, and we don't see pulses. These objects, often called radio-quiet neutron stars, or simply isolated neutron stars, are much harder to detect. They can only be found through their thermal emission. They're hot enough, at temperatures of a few million degrees, to emit X-rays. The Hubble Space Telescope and X-ray observatories have identified several dozen of these isolated neutron stars, though many more certainly exist undetected. Binary systems where a neutron star has a companion star create unique situations. If the companion is a normal star and the orbit is close enough, the neutron star's gravity can pull material from the companion. This material spirals inward through an accretion disk, heating to millions of degrees and emitting intense X-rays before crashing onto the neutron star's surface. These X-ray binaries can be incredibly luminous, sometimes outshining entire galaxies in X-rays. The infalling material also carries angular momentum, spinning up the neutron star. Over millions of years, an old, slow-spinning pulsar can be recycled into a millisecond pulsar, rotating hundreds of times per second, rejuvenated by mass transfer from its companion. When two neutron stars orbit each other, they form a binary neutron star system. Objects like the Hulse-Taylor binary, discovered by Russell Hulse and Joseph Taylor in 1974, which earned them the 1993 Nobel Prize in Physics. These systems emit gravitational waves, ripples in spacetime that carry away orbital energy. As they lose energy, the neutron stars spiral closer together. Eventually, after millions or billions of years, they merge in a catastrophic collision. The merger produces intense gravitational waves, events that LIGO and other gravitational wave observatories have detected, along with a kilonova, a spectacular explosion that creates heavy elements like gold and platinum through rapid neutron capture. The merger of two neutron stars can produce different outcomes depending on the total mass. If the combined mass is below about 2.2 to 2.9 solar masses, the exact threshold remains uncertain. The merger might create a more massive neutron star, though one that's likely unstable and will soon collapse. If the total mass exceeds this threshold, the merger immediately creates a black hole, with no stable neutron star phase at all. The LIGO detection in 2017, designated GW170817, appears to have created either a hypermassive neutron star that collapsed within seconds or a black hole directly. If the collapsing core of a supernova exceeds about 2.2 to 3 solar masses, again, the exact threshold depends on the poorly known equation of state of nuclear matter. Neutron degeneracy pressure cannot halt the collapse. Nothing known in physics can support the core against its own gravity. The collapse continues, compressing matter to infinite density at a point called a singularity, surrounded by an event horizon from which nothing can escape. The stellar remnant becomes a black hole. The supernova explosion might proceed normally, leaving a black hole at the center of the expanding debris. Or if the core is sufficiently massive, the collapse might be so catastrophic that it swallows the infalling material before an explosion can develop, creating a black hole with little or no visible supernova, a so-called failed supernova. Stellar mass black holes created from supernova typically contain 5 to perhaps 20 solar masses. They're invisible except through their gravitational effects and the radiation from material falling into them. In X-ray binary systems, black holes reveal themselves through the extremely energetic X-rays emitted by infalling material, distinguishable from neutron star systems by the absence of pulsations and by the inferred mass. Anything above 3 solar masses cannot be a neutron star and must be a black hole. Some supernova types leave nothing behind at all. Pair instability supernova occur in extremely massive stars, those with initial masses exceeding about 130 solar masses. In the cores of these giants, temperatures and photon energies become so extreme that gamma-ray photons spontaneously convert into electron-positron pairs. This pair production removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is obliterated. No neutron star, no black hole, just an expanding cloud of debris. These explosions were more common in the early universe, when stars could grow more massive due to lower metallicity, but they might still occur in regions with primordial composition. The observable supernova remnant, the expanding shell of gas and dust, evolves over thousands to tens of thousands of years. Initially, the blast wave plows through the surrounding interstellar medium at thousands of kilometers per second, creating a hot, shock-heated region. The Crab Nebula, the remnant of the 1054 supernova, is still expanding at about 1,500 kilometers per second. The pulsar at its center powers the nebula's glow, creating a wind of relativistic particles that illuminate the expanding gas. Older supernova remnants like the Cygnus Loop, about 10,000 years old, have expanded to hundreds of light years across. The blast wave has slowed to tens of kilometers per second, and the shock is transitioning from adiabatic expansion, where the remnant retains its heat, to radiative expansion, where the shocked gas cools and radiates energy away, creating the delicate filaments visible in optical and X-ray images. Eventually, after perhaps 100,000 years, the remnant merges with the surrounding interstellar medium, its expansion slowing to match the general motion of gas in the galaxy. The enriched material, oxygen, carbon, silicon, iron, and other elements forged in the star and the explosion, mixes into interstellar clouds. These enriched clouds eventually collapse to form new generations of stars and planets, incorporating the elements created by the previous stellar generation. Every atom of oxygen you breathe, every atom of carbon in your body, was created in a star and dispersed by a supernova, later incorporated into the molecular cloud from which the Sun and Earth formed. What's left after a star explodes depends on the fine details of mass, composition, rotation, and magnetic fields, whether the core becomes a neutron star or black hole, whether the neutron star becomes an observable pulsar or remains radio quiet, whether the magnetic field is ordinary or reaches magnetar strength. Each stellar death creates a unique remnant, a compact object encoding in its properties the history of the parent star and the violence of its death, objects that will persist for trillions of years after the last stars have formed, cooling slowly in the expanding universe, monuments to stellar death that simultaneously mark endings and beginnings in the grand cycle of cosmic recycling. Why alien life might not use DNA, deoxyribonucleic acid, is the molecule of heredity for nearly all life on Earth. From bacteria to blue whales, from mushrooms to sequoia trees, every organism uses DNA to store genetic information, to pass traits from parents to offspring, and to direct the construction of proteins that build and maintain living cells. DNA's structure is elegant and famous, a double helix of two strands twisting around each other, each strand composed of a sugar phosphate backbone with 4 types of bases attached in sequences that encode genetic instructions. DNA seems so fundamental to life that it's easy to assume it must be universal, that any living thing anywhere in the universe would use DNA. But this assumption is almost certainly wrong. DNA is not the only molecule capable of storing and transmitting genetic information, and the specific chemistry that makes DNA work on Earth might not be optimal or even possible under different planetary conditions. To understand why alien life might not use DNA, we first need to understand what DNA actually does and what properties make it suitable for its role. DNA serves 3 critical functions. First, it stores information. The sequence of bases along the DNA strand encodes instructions for building proteins and regulating cellular processes. Second, it replicates. DNA can be copied with reasonable accuracy, allowing genetic information to be passed from one generation to the next. Third, it allows variation. Copying isn't perfect, and occasional errors introduce mutations that create the genetic diversity necessary for evolution. But DNA is not unique in performing these functions. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information, be copied, and undergo evolution despite having different chemical structures than DNA. These molecules use different sugars in their backbones, 3 O's instead of deoxyribose, locked nucleic acids with modified sugars, or even molecules with completely different backbone structures. These XNAs can form base pairs, store sequences of information, and be replicated by specialized enzymes. They demonstrate conclusively that DNA is not the only possible genetic molecule, merely the one that happened to work on Earth. The chemistry of DNA is optimized for Earth's conditions. DNA is stable in liquid water at temperatures roughly between 0 and 40 degrees Celsius, the temperature range where most Earth life operates. The hydrogen bonds holding the 2 strands together are strong enough to keep the double helix intact, but weak enough that the strands can be separated for copying. The sugar phosphate backbone is stable in water at neutral pH, but can be broken down by enzymes when necessary. The bases, adenine, thymine, guanine, and cytosine, are moderately stable molecules that can withstand normal cellular conditions, but can be damaged by extreme heat, intense radiation, or strongly acidic or alkaline environments. On a planet with very different conditions, DNA might not function well or at all. Consider a world much hotter than Earth, perhaps a planet orbiting very close to its star, with surface temperatures exceeding 100 degrees Celsius, but with liquid water kept stable by extreme atmospheric pressure. At these elevated temperatures, DNA becomes increasingly unstable. The hydrogen bonds holding the 2 strands together weaken and break more easily. The chemical bonds in the bases and the backbone break down more rapidly. Organisms on such a world would need genetic molecules more heat-resistant than DNA, perhaps with stronger chemical bonds, more stable base structures, or completely different architectures that maintain integrity at high temperatures. Some Earth organisms that thrive in extreme heat have evolved DNA repair mechanisms that constantly fix damage to their genetic material, but there are limits to how hot DNA can tolerate. Beyond a certain temperature, the rate of damage exceeds the capacity of repair mechanisms to fix it. Alien life on a hot world might evolve an alternative genetic molecule with inherently greater thermal stability, perhaps using bases with stronger bonding, or sugars that resist thermal degradation, or entirely different building blocks that remain stable at temperatures where DNA would fall apart within seconds. At the opposite extreme, very cold worlds present different challenges. DNA becomes more rigid at low temperatures, making it harder to separate the strands for copying. The enzymes that copy DNA become less efficient or stop working entirely when too cold. Life on an extremely cold world, perhaps on a moon like Titan, where temperatures hover around -180 degrees Celsius, would need genetic molecules that remain flexible and functional at these frigid temperatures. The chemistry would necessarily be different from DNA, which was shaped by evolution to function in Earth's moderate temperature range. The solvent environment profoundly affects what genetic molecules are possible. DNA functions in liquid water, and its chemical properties are specifically suited to aqueous environments. The sugar phosphate backbone is hydrophilic, attracted to water, which helps keep DNA dissolved in cellular fluids. The bases are hydrophobic, repelled by water, which helps drive base pairing by pushing bases toward each other and away from the surrounding water. This balance creates DNA's structure and stability. In a different solvent, liquid methane, liquid ammonia, or something even more exotic, DNA's chemistry wouldn't work the same way. Water's polarity, its hydrogen bonding capacity, its ability to dissolve certain substances while excluding others. All these properties shape how DNA behaves. In liquid methane, a non-polar solvent, molecules that are hydrophobic in water might become soluble, while hydrophilic molecules might be insoluble. A genetic molecule designed for a methane-based solvent would need completely different chemical properties than DNA, perhaps with non-polar groups exposed to interact with the methane solvent, and polar groups hidden in the molecule's interior. The availability of raw materials constrains what genetic molecules can be built. DNA requires phosphorus, nitrogen, carbon, oxygen, and hydrogen. Phosphorus, though essential for DNA's backbone, is relatively rare in the universe compared to lighter elements. A planet poor in phosphorus might not be able to build DNA-like molecules and would need to evolve genetic systems based on more abundant elements. Perhaps silicon could replace phosphorus in the backbone, or sulfur could play a role, or arsenate, a chemical similar to phosphate, might substitute. Though experiments with arsenate-based DNA on Earth showed it's much less stable than normal DNA. The 4-base system used by DNA, adenine, thymine, guanine, and cytosine, is not the only possible coding scheme. RNA, DNA's chemical cousin, uses uracil instead of thymine, demonstrating that the specific bases aren't fixed. In principle, genetic molecules could use 3 bases, or 6, or even more. More bases would allow more information to be encoded in shorter sequences. With 4 bases, each position in the sequence can encode 2 bits of information, but with 8 bases, each position could encode 3 bits. An alien genetic system might use more or fewer bases depending on what works best with its chemistry. Some scientists have even created expanded genetic alphabets, DNA-like molecules with additional base pairs beyond the natural 4. These synthetic genetic systems can store more information per unit length than natural DNA and can be copied by modified enzymes. The existence of these expanded alphabets demonstrates that the 4-base system is not uniquely optimal, but rather reflects the specific chemistry that evolved on Earth. Alien life might independently evolve genetic systems with different numbers of bases encoding information in different ways. The structure of the genetic molecule might differ radically from DNA's double helix. DNA forms a helix because of how the bases pair and how the sugar phosphate backbone bends, but other structures are possible. Some XNAs form helices with different geometries, left-handed instead of right-handed, wider or narrower than DNA, with more or fewer base pairs per helical turn. Some synthetic genetic molecules don't form helices at all, but adopt completely different 3-dimensional structures. An alien genetic molecule might be a triple helix, a quadruple helix, a ladder without a twist, or some topology we haven't imagined. The copying mechanism might also differ. DNA is copied by enzymes called polymerases that move along the DNA strand, reading the sequence and creating a complementary new strand. This process requires a complex molecular machinery that evolution has refined over billions of years on Earth. Alien life might evolve completely different copying mechanisms, perhaps catalytic RNA-like molecules that copy themselves without protein enzymes, or inorganic crystals that template the formation of complementary structures, or even copying processes that don't involve template-directed synthesis at all, but rather some form of self-assembly guided by the genetic molecule structure. The rate of mutation, how often copying errors occur, affects evolution's pace. DNA polymerases on Earth make errors at a rate of roughly 1 mistake per billion bases, copied for the most accurate enzymes, though rates vary. This error rate is low enough to preserve genetic information across generations, but high enough to generate the variation necessary for evolution. Alien genetic systems might have very different error rates. A system with much lower error rates would evolve more slowly, potentially making adaptation difficult. A system with higher error rates might generate variation faster, but risk genetic information degradation. The optimal error rate depends on generation time, selection pressure, and environmental stability. RNA represents an alternative genetic molecule that exists on Earth and might have preceded DNA in evolution. RNA can store information, catalyze chemical reactions, and replicate all functions DNA cannot perform alone. The RNA world hypothesis proposes that early life used RNA as both genetic material and catalytic molecule before DNA and proteins evolved. An alien world might develop life that remains in an RNA world-like state, never evolving DNA, or might evolve RNA into forms more sophisticated than anything on Earth, creating genetic systems based on elaborate RNA structures rather than DNA. Some scientists have speculated about non-molecular genetic systems. Perhaps information could be stored in the crystal structure of inorganic minerals, with patterns of inclusions, defects, or layering encoding information that could be replicated when crystals grow and form templates for new crystals. Or perhaps information could be stored in magnetic domains in iron-rich minerals, with the orientation of magnetic fields encoding genetic instructions. These ideas are highly speculative and face enormous challenges. How would such systems be read and translated into functional structures? But they illustrate that genetic information storage might not require organic molecules at all. The universality of certain aspects of information storage might transcend specific chemistry. Any genetic system, whether based on DNA, XNA, RNA, or something entirely different, must be able to store discrete, sequential information, symbols arranged in order that can be read and interpreted. This is fundamentally a problem of information theory rather than chemistry. The specific physical substrate that stores the information might be less important than the information itself, and the mechanisms for reading, copying, and translating it into functional structures. If we ever detect alien life, determining its genetic system would be among the first questions we'd want to answer. If alien life uses DNA with the same 4 bases and same genetic code as Earth life, it would suggest either that DNA is universally optimal, unlikely given all the possible alternatives, or that Earth life and alien life share a common origin, perhaps through panspermia. The hypothesis that life can spread between worlds via meteorites or comets, finding alien life with completely different genetic molecules would confirm that life can independently originate using different chemistry, revealing that DNA is merely one solution among many to the problem of heredity. The genetic code, the mapping between base sequences and amino acids, might also differ. Earth's genetic code is nearly universal across all life, with 3 base sequences called codons specifying which amino acid to insert when building proteins. But the specific assignment of codons to amino acids appears somewhat arbitrary. There's nothing inherent in the chemistry of the codon UUU that demands it code for the amino acid phenylalanine rather than some other amino acid. The code seems to be a frozen accident. Once it was established early in evolution, changing it would be catastrophic because it would alter the meaning of every gene, so it became locked in place. Alien life would likely evolve a completely different genetic code, with different codon assignments, and possibly even a different codon length. 2 base codons, or 4 base codons, or variable length codons. Why alien life might not use DNA comes down to DNA being a solution specific to Earth's conditions: liquid water at moderate temperatures, specific pH ranges, availability of particular elements, and the accidents of chemical evolution that occurred during life's origin on our world. Different conditions would favour different molecules, and even similar conditions might allow evolution to discover different solutions. DNA is remarkable and elegant, but it's not magic or inevitable. It's chemistry, sophisticated, evolved chemistry that works beautifully on Earth, but that represents just one possible answer to the fundamental question of how to store, copy, and transmit genetic information across generations. Across the universe, life might employ countless different genetic systems, each one adapted to its world's unique conditions, each one encoding information and enabling heredity through different molecular mechanisms, proving that while the principle of heredity might be universal wherever life exists, the specific molecular machinery implementing that heredity can vary as widely as the diversity of worlds themselves, with DNA being merely Earth's particular solution to the universal challenge of passing genetic information from parent to offspring through the generations. What is dark matter, and why can't we see it? Imagine trying to understand a conversation in a crowded room while wearing earplugs. You can see people's mouths moving, see their gestures, watch them react to each other, but you can't hear the words being spoken. You know communication is happening, the evidence is clear in the movements and responses, but the medium of that communication remains completely inaccessible to you. This is somewhat like humanity's relationship with dark matter. We can see its effects throughout the universe, observe how it shapes galaxies and bends light, measure its gravitational influence on everything around it. Yet the substance itself remains invisible and intangible to every instrument we've built to observe the cosmos. Dark matter makes up approximately 85% of all matter in the universe. Let that sink in for a moment. Everything you can see, every star, every galaxy, every glowing nebula, every planet, every atom in your body represents only about 15% of the matter that exists. The rest, the overwhelming majority, is dark matter, and it surrounds us, permeates us, flows through us, yet reveals itself only through its gravitational effects. The story of dark matter's discovery begins not with a sudden revelation, but with decades of observations that didn't quite make sense. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving within the cluster and used these velocities to calculate how much mass must be present to keep the cluster gravitationally bound. What he found was shocking. The galaxies were moving so fast that they should have escaped the cluster's gravity and flown apart long ago, unless the cluster contained far more mass than could be seen in the form of stars and gas. Zwicky proposed that some form of dark matter must exist, matter that didn't emit light, but provided the additional gravity needed to hold the cluster together. His idea was largely ignored for decades. It seemed too radical, too strange. Surely there was a simpler explanation. Perhaps astronomers were just missing some normal matter, dust clouds or dim stars that hadn't been detected yet. but the evidence kept accumulating. In the 1970s, astronomer Vera Rubin conducted detailed studies of how stars and gas move within spiral galaxies. According to the laws of gravity and orbital mechanics, objects farther from the center of a galaxy should move more slowly, just as planets farther from the Sun orbit more slowly than those closer in. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 years to complete one orbit. The same principle should apply to galaxies. Stars near the edge should crawl along in their orbits compared to stars closer to the galactic center. But that's not what Rubin found. She observed that stars at the outer edges of galaxies move just as fast as stars closer to the center, sometimes even faster. The rotation curves of galaxies were flat rather than declining, which could only mean one thing: there was far more mass in these galaxies than could be accounted for by visible stars and gas. And this extra mass wasn't concentrated at the center where most of the visible matter was. It extended far beyond the visible disk, forming a massive spherical halo of invisible matter surrounding each galaxy. Picture a galaxy in your mind, a spiral with graceful arms of stars spinning around a bright central bulge. Now imagine that entire visible structure is embedded within a much larger sphere of dark matter, extending perhaps 10 times farther than the visible stars reach. This dark matter halo contains several times more mass than all the stars, gas and dust combined, yet it emits no light, no radio waves, no X-rays, nothing we can detect directly. The evidence for dark matter extends far beyond galaxy rotation curves. Gravitational lensing provides some of the most compelling proof. According to Einstein's theory of general relativity, mass warps the fabric of spacetime, and light follows the curves in this warped spacetime. When light from a distant galaxy passes near a massive object, its path bends, just as light bends when passing through a glass lens. The amount of bending depends on how much mass is present. Astronomers observe light from distant galaxies being bent and distorted as it passes through galaxy clusters. By measuring this distortion carefully, they can map out exactly where mass is concentrated in these clusters, creating what's essentially a gravity map. When they do this, they find that most of the mass, about 90%, isn't where the visible galaxies are. It's distributed in a much larger structure, consistent with massive halos of dark matter. One of the most dramatic examples came from studying a structure called the Bullet Cluster, where two galaxy clusters had collided and passed through each other. During the collision, the hot gas from each cluster, which is normal matter, slowed down and remained near the collision site, heated by the impact. But the dark matter from each cluster, which doesn't interact with normal matter except through gravity, passed right through and continued moving. By mapping the gravity through gravitational lensing, astronomers could see that most of the mass had separated from the visible gas, providing direct evidence that dark matter and normal matter are distinct substances. So what is dark matter made of? This is one of the deepest mysteries in physics. And the honest answer is that we don't know. We know what it isn't. It's not made of atoms, protons, neutrons, or electrons. It's not any form of normal matter that we're familiar with. We call normal matter baryonic matter, and dark matter is something entirely different, something that exists outside the catalogue of particles that make up everything we can touch and see. The most popular hypothesis is that dark matter consists of particles that simply don't interact with electromagnetic radiation. Light, radio waves, X-rays, any form of light across the entire spectrum. These hypothetical particles, often called WIMPs, weakly interacting massive particles, would have mass and exert gravity, but they wouldn't emit, absorb, or reflect light. They would be essentially transparent to electromagnetic radiation, which is why we can't see them. Imagine a particle that could pass through matter almost as if it weren't there. Billions of these particles might be flowing through your body right now. passing through the Earth, streaming through space, and you would never know. They don't collide with atoms, don't scatter off electrons, don't leave any trace except for their collective gravitational influence. This is what dark matter particles would be like. Ghost particles that fill the universe, but interact with normal matter only through the weakest of forces. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and background radiation, trying to catch the rare interaction of a dark matter particle with normal matter. These detectors contain tanks of specially purified materials, cooled to near absolute zero, instrumented with sensors that can detect the tiniest energy deposit. The idea is that occasionally, very rarely, a dark matter particle might collide with a nucleus in the detector, releasing a tiny amount of energy that could be measured. So far, despite decades of searching with increasingly sensitive experiments, no one has definitively detected a dark matter particle. Another possibility is that dark matter consists of primordial black holes that formed in the early universe, not from collapsing stars, but from density fluctuations shortly after the Big Bang. These would be dark by their very nature, since black holes don't emit light. However, careful observations suggest that primordial black holes can't account for all the dark matter. They would produce observable effects, like gravitational microlensing when they pass in front of distant stars, and we don't see these effects at the level that would be expected if most dark matter were in this form. Some theories propose that dark matter might be axions, extremely light particles that were produced in enormous quantities in the early universe. These would be very different from WIMPs, much lighter, much more numerous, behaving more like a wave than individual particles. Detecting axions requires different experimental approaches, and several experiments are currently searching for these elusive particles. There's even a possibility, though most physicists consider it less likely, that dark matter doesn't exist at all. Instead, perhaps our understanding of gravity is incomplete, and the theory needs to be modified to explain the observations without requiring invisible matter. These modified gravity theories, called MOND, modified Newtonian dynamics, and various relativistic extensions, can explain some observations but struggle with others, like the bullet cluster, which seems to require actual dark matter to explain. Dark matter played a crucial role in the formation of structure in the universe. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. These variations were the seeds of all future structure: galaxies, galaxy clusters, and the cosmic web. But normal matter coupled to radiation in the early universe couldn't collapse and clump together efficiently. Dark matter, which didn't interact with radiation, could begin collapsing earlier, forming gravitational wells that normal matter eventually fell into. Without dark matter, galaxies as we know them couldn't have formed in the time available since the Big Bang. Today, dark matter continues to shape the universe. It forms the gravitational scaffolding along which galaxies are distributed. It determines how galaxy clusters form and evolve. It affects how galaxies merge and interact. Every large-scale structure in the universe exists because of dark matter's gravitational influence. On smaller scales, dark matter fills our own galaxy. The Milky Way sits within a dark matter halo that extends far beyond the visible disk of stars. This halo contains perhaps 10 times more mass than all the stars in the galaxy. As our solar system orbits the galactic center, we're moving through this sea of dark matter. At any given moment, thousands of dark matter particles might be passing through every cubic centimeter of space, though detecting even one of them remains beyond our current capabilities. The invisibility of dark matter is not a limitation of our instruments. It's a fundamental property of the substance itself. We can't see it because it doesn't interact with light in any way. We can't build a better telescope or a more sensitive camera to observe it directly. The only way we know it exists is through its gravitational effects on the things we can see. It reveals itself in the motion of stars, the bending of light, the structure of the cosmic web, and the evolution of the universe itself. Dark matter surrounds us, shapes the cosmos, and yet remains one of the deepest mysteries in science, a reminder that the universe is far stranger and more complex than our everyday experience might suggest. Why distant galaxies? Look red. When astronomers point their most powerful telescopes toward the deepest reaches of space, photographing galaxies billions of light years away, they notice something remarkable. These distant galaxies appear distinctly redder than nearby ones. Light that was emitted as ultraviolet or blue has been shifted toward red and infrared wavelengths by the time it reaches Earth. This redshift is one of the most important observations in all of astronomy, providing direct evidence for the expansion of the universe and allowing astronomers to measure cosmic distances and trace the history of the cosmos back nearly to the Big Bang itself. The primary cause of this reddening is cosmological redshift, a consequence of the universe's expansion. This phenomenon was first observationally established by Edwin Hubble in 1929, though the theoretical groundwork had been laid by several physicists, including Alexander Friedmann and Georges Lemaitre, who independently developed solutions to Einstein's equations of general relativity that predicted an expanding universe. Hubble observed that distant galaxies showed spectral lines, the characteristic fingerprints of elements absorbing or emitting light at specific wavelengths, shifted toward longer, redder wavelengths. Moreover, he found that more distant galaxies showed larger redshifts, establishing what became known as Hubble's law. The recession velocity of a galaxy is proportional to its distance. The expansion of the universe is not like objects moving through space. It's space itself that's expanding. Imagine the universe as the surface of a balloon with galaxies painted on it. As you inflate the balloon, the surface stretches and the distance between any 2 points on the surface increases. The galaxies themselves don't move through the rubber. The rubber itself expands, carrying the galaxies apart. This is fundamentally different from regular motion through space, and it's this expansion of space that creates cosmological redshift. When a galaxy emits light, that light begins its journey through space toward Earth. The light consists of electromagnetic waves, oscillating electric and magnetic fields propagating through space. As the light travels, the space through which it's traveling is expanding. This expansion stretches the wavelength of the light. Imagine a wave painted on a rubber band. If you stretch the rubber band, the wave gets stretched too, its wavelength increasing. The same thing happens to light traveling through expanding space. Light that began as ultraviolet with a wavelength of 300 nanometers might arrive at Earth as visible red light with a wavelength of 600 nanometers if it has traveled through enough expanding space. The amount of redshift depends on how much the universe has expanded during the light's journey. Astronomers quantify this using the redshift parameter, represented by the letter Z. A redshift of Z equals 1 means the universe has doubled in size since the light was emitted. Wavelengths have stretched by a factor of 2. A redshift of Z equals 2 means the universe has tripled in size. Wavelengths have stretched by a factor of 3. The highest redshift galaxies yet observed have redshifts around Z equals 13 to 14, meaning the universe has expanded by a factor of about 14 or 15 since those galaxies emitted the light we now detect. These galaxies existed when the universe was only a few 100 million years old, less than 3% of its current age. For nearby galaxies, the redshift is small, perhaps Z equals 0.01 or less. The Andromeda galaxy, our nearest large galactic neighbour, actually shows a blue shift rather than a red shift, because it's moving toward us through space faster then the cosmic expansion is carrying it away. But for galaxies more than a few hundred million light-years distant, cosmological redshift dominates. And the farther the galaxy, the larger the redshift. This relationship between distance and redshift allows astronomers to use redshift as a distance indicator. By measuring the redshift of spectral lines in a galaxy's light, they can calculate how far away it is and how long ago the light was emitted. A galaxy at z equals 1 is seen as it was about 8 billion years ago, when the universe was roughly half its current age. A galaxy at z equals 6 is seen as it was less than a billion years after the Big Bang, when the universe was still in its infancy and the first generations of stars were forming. Redshift affects all wavelengths equally, in terms of the stretching factor. Ultraviolet light gets stretched into visible light. Visible light gets stretched into infrared. Infrared gets stretched into far infrared and eventually into microwaves. For the most distant galaxies, light that was emitted in the ultraviolet, the signature of hot, young stars, arrives at Earth as infrared radiation. This is why infrared telescopes, like the James Webb Space Telescope, are so valuable for studying the early universe. They can detect the stretched light from the most distant galaxies, galaxies so far away that their visible light has been redshifted entirely out of the visible spectrum. There's another related effect that makes distant galaxies appear redder beyond just the stretching of wavelengths. As light loses energy through redshift, longer wavelengths mean lower energy. The apparent brightness of the galaxy dims. A galaxy at high redshift appears fainter than it would if there were no cosmic expansion. Additionally, the rate at which photons arrive is reduced. If a galaxy emits 1 photon per second toward Earth, but the universe doubles in size during the light's journey, those photons arrive spread out over 2 seconds because the space between them has been stretched. This reduces the detected brightness even further. The cosmic microwave background radiation provides the most extreme example of cosmological redshift. This radiation was emitted when the universe was 380,000 years old, at a temperature of about 3,000 Kelvin. At that temperature, matter emitted primarily visible and infrared radiation. The redshift since that time is about c equals 1,100, meaning the universe has expanded by a factor of 1,100. Wavelengths have been stretched by the same factor, so light that was visible orange or red has been stretched into microwave radiation. The temperature corresponding to this radiation has dropped by the same factor, from 3,000 Kelvin down to 2.7 Kelvin today. It's important to distinguish cosmological redshift from Doppler shift, though they're related and can sometimes be confused. Doppler shift occurs when a light source moves through space toward or away from an observer. An approaching object's light is blue shifted, compressed to shorter wavelengths, while a receding object's light is redshifted. This is the effect that changes the pitch of a siren as an ambulance approaches and then passes you. For galaxies with relatively small redshifts, say z less than 0.1, cosmological redshift and Doppler shift give nearly identical results and can be treated interchangeably for many purposes. But for high redshifts, the distinction matters. Cosmological redshift is fundamentally about the expansion of space itself, while Doppler shift is about motion through space. Redshift also allows astronomers to study the history of cosmic expansion. By measuring redshifts of many galaxies at various distances and determining their distances through other methods, like standard candles, objects of known intrinsic brightness, astronomers can trace how the expansion rate has changed over cosmic history. These studies revealed one of the most surprising discoveries in modern cosmology. The expansion of the universe is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery, made by studying distant supernovae and measuring how their redshifts and distances deviated from what would be expected in a universe with constant or decelerating expansion. The acceleration implies the existence of dark energy, a mysterious component that makes up about 68% of the universe's total energy density and exerts a kind of repulsive effect that pushes space apart. This dark energy's influence has grown over cosmic time as the universe expanded and matter became more dilute. In the early universe, matter dominated and the expansion was slowing down. But a few billion years ago, dark energy became dominant and the expansion began accelerating. Distant galaxies' redshifts encode this history, showing patterns that reveal when the transition from deceleration to acceleration occurred. Redshift measurements also reveal structure in the universe. When astronomers measure redshifts for thousands or millions of galaxies, they can create three-dimensional maps showing how galaxies are distributed in space. These maps reveal the cosmic web, the filaments, walls, and voids that constitute the large-scale structure of the universe. Regions where galaxies are closely spaced show similar redshifts because they are at similar distances. Voids show up as redshift ranges where few galaxies appear. The chemical evolution of the universe is written in redshift as well. Spectroscopy of distant galaxies reveals what elements were present when that light was emitted billions of years ago. By comparing galaxies at different redshifts, different cosmic times, astronomers can trace how the abundance of heavy elements has increased over cosmic history as successive generations of stars created these elements through nuclear fusion and dispersed them through supernova explosions. Galaxies at Z equals 6 or 7 show much lower abundances of elements heavier than helium compared to nearby galaxies, confirming that the early universe was primarily hydrogen and helium, with heavy elements accumulating over billions of years. Even the shapes and types of galaxies change with redshift. High redshift galaxies tend to be smaller, more irregular, and more actively forming stars than low redshift galaxies. This reveals that galaxies evolve over time, growing through mergers and gradually building up their stellar populations. The universe at Z equals 2, when it was about 3 billion years old, was a much more turbulent place, with higher rates of galaxy interactions and star formation than the relatively sedate local universe we see today. Gravitational lensing affects redshift measurements in subtle ways. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity bends the light's path and can magnify the image. But it also affects the light's frequency. Different images of a gravitationally lensed galaxy, formed by light taking different paths around the lensing mass, can show slightly different redshifts due to the gravitational time dilation in the lens's gravitational field. These tiny differences help astronomers probe the distribution of mass in the lensing object. The reddening of distant galaxies is therefore not just an interesting observational fact, but a fundamental window into cosmic history. Every measurement of a galaxy's redshift tells us how far away it is, how long ago its light was emitted, and what the universe was like at that cosmic epoch. The systematic increase in redshift with distance directly demonstrates that the universe is expanding, that it had a beginning in the Big Bang, and that it's evolving over time. The precise pattern of redshifts reveals the expansion history, constrains the properties of dark energy, and allows us to trace the formation and evolution of structure across billions of years of cosmic time, making the reddening of distant galaxies one of the most information-rich phenomena in observational astronomy. Where baby stars come from. Stars are not born in the bright, empty spaces between galaxies or in the clear voids of interstellar space. They emerge from darkness, from vast clouds of gas and dust that hang in the spiral arms of galaxies, regions so dense with obscuring material that they appear as black patches against the glowing background of the Milky Way. These stellar nurseries, called molecular clouds, are the cosmic wombs where stars begin their lives, places where gravity, temperature, pressure, and chemistry conspire to transform diffuse gas into brilliant spheres of nuclear fusion that will shine for millions or billions of years. The process begins with a molecular cloud, an enormous accumulation of gas and dust drifting through the galaxy. These clouds are cold, typically only 10 to 20 degrees above absolute zero, and they're composed primarily of molecular hydrogen, two hydrogen atoms bonded together, mixed with helium and trace amounts of heavier elements. The clouds also contain dust grains, tiny particles of silicates and carbon compounds, each grain smaller than a bacterium, but collectively making up about 1% of the cloud's mass. These dust grains play a crucial role despite their small mass contribution, shielding the interior of the cloud from starlight and cosmic rays, allowing it to remain cold enough for molecules to survive. Molecular clouds range in size from relatively small clouds, a few light years across, to giant molecular cloud complexes spanning hundreds of light years and containing enough material to form hundreds of thousands of stars. The Orion Molecular Cloud Complex, one of the nearest star-forming regions at about 1,300 light-years from Earth, contains enough gas to make roughly 100,000 stars, like the Sun. The cloud extends across much of the constellation Orion, with the famous Orion Nebula marking just one small region where star formation is particularly active and visible. For stars to form, something must disturb these clouds, compressing them beyond a critical threshold where gravity overwhelms the internal pressure that normally keeps the cloud stable. This compression can come from several sources. A shockwave from a supernova explosion, traveling through space at thousands of kilometers per second, can slam into a molecular cloud and compress it. The spiral density waves that create the spiral arms of galaxies compress gas as it enters these regions, triggering star formation that lights up the spiral arms with young, bright stars. Even the radiation and stellar winds from existing massive stars can compress surrounding gas, triggering new generations of star formation in a process that propagates through the cloud. Once a region of the cloud is compressed, gravity takes control. The denser parts of the cloud pull in surrounding material, growing denser still. This runaway process would cause the entire cloud to collapse into one enormous star, but molecular clouds are turbulent places, filled with eddies and currents of gas flowing in different directions. This turbulence, combined with the cloud's rotation and magnetic fields threading through it, breaks the cloud into fragments, each fragment typically containing anywhere from a fraction of a solar mass to tens of solar masses, becomes the seed of a star or a small system of stars. As a fragment collapses, it heats up. This might seem counterintuitive. How does something heat up as it collapses in the cold of space? The answer lies in gravitational potential energy. As gas falls inward, it accelerates, gaining kinetic energy. When fast-moving atoms and molecules collide with other particles, they convert their kinetic energy into thermal energy, heat. The center of the collapsing fragment grows hotter and denser, while the outer regions continue to fall inward, feeding the growing concentration at the center. The collapse doesn't proceed smoothly or uniformly. The fragment rotates, inherited from the overall rotation of the molecular cloud, and conservation of angular momentum means it spins faster as it shrinks, just as an ice skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the center. Instead, material settles into a rotating disk around the growing protostar, the nascent star at the center. This disk, called a protoplanetary disk or protostellar disk, channels material toward the protostar, while the outer parts remain in orbit, eventually becoming the raw material from which planets might form. The young protostar, deeply embedded in the infalling gas and dust, is invisible at optical wavelengths. The surrounding cocoon of material absorbs any visible light the protostar emits and re-radiates it as infrared radiation. This is why infrared telescopes are essential for studying star formation. They can penetrate the dust and observe the protostars hidden within molecular clouds. The Spitzer Space Telescope and now the James Webb Space Telescope have revealed thousands of these embedded protostars, showing snapshots of stars at various stages of formation. As the protostar continues to accrete mass, its central temperature and pressure climb steadily. The journey from cold molecular gas to a hot protostar takes roughly 100,000 years for a Sun-like star, though this timescale varies depending on the protostar's mass. More massive protostars collapse more quickly because their stronger gravity accelerates the infall. Less massive protostars take longer, sometimes millions of years, to fully form. The protostar doesn't simply accrete all the material that falls toward it. Young protostars are violent, magnetically active objects. Magnetic field lines threading through the protostar, and its disk can become twisted and tangled by the rotation. And these magnetic fields launch jets, narrow beams of gas that shoot outward from the protostar's poles at speeds of hundreds of kilometers per second. These jets are one of the most distinctive signs of active star formation. The Hubble Space Telescope has captured stunning images of these jets, often light years long, streaming away from young stars still hidden within their dusty cocoons. The jets serve an important function. They carry away angular momentum and energy that would otherwise prevent further accretion. Without some mechanism to remove angular momentum, the disk would simply spin faster and faster, and material would stop falling onto the protostar. The jets, along with stellar winds, outflows of gas from the protostar's surface, solve this problem, allowing the protostar to continue growing even as it spins. Where the jets slam into the surrounding molecular cloud, they create glowing knots and filaments called Herbig-Haro objects, named after astronomers George Herbig and Guillermo Haro, who studied them in the 1950s. These objects glow because the jet's high-speed collision with the ambient gas heats it to thousands of degrees, causing atoms to emit light. Herbig-Haro objects can move visibly over timescales of years, and they serve as signposts marking regions of active star formation. The accretion phase lasts for roughly 1 million years, though again this varies with stellar mass. During this time, the protostar is not yet a true star because no nuclear fusion occurs in its core. It shines from gravitational energy. The energy released as material falls onto its surface, and as it slowly contracts under its own weight. This contraction, described by Hermann von Helmholtz and Lord Kelvin in the 19th century, heats the interior gradually. Eventually, after millions of years of contraction and heating, the core temperature reaches approximately 10 million degrees Celsius. At this critical temperature, protons moving at extremely high speeds collide with enough energy to overcome their mutual electrical repulsion and fuse together, creating helium and releasing energy. This ignition of hydrogen fusion marks the birth of a true star. The protostar becomes a main sequence star, entering a stable phase where the energy released by fusion creates outward pressure that balances gravity's inward pull. For a star like the Sun, this moment arrives roughly 10 million years after the initial collapse began. The newly formed star is now generating its own energy through nuclear reactions rather than relying on gravitational contraction. It will remain on the main sequence, fusing hydrogen in its core for about 10 billion years, 100 times longer than it took to form. Not all fragments in a molecular cloud form single stars. Many form binary or multiple star systems where two or more stars orbit each other. The fragmentation process can produce two separate cores within a single disk, each growing into a star. Or a protostellar disk can become gravitationally unstable and fragment, forming additional stars. About half of all stars exist in binary or multiple systems, making our single sun somewhat unusual. The smallest fragments don't have enough mass to ever ignite hydrogen fusion. Objects below, about 0.08 solar masses, roughly 80 times Jupiter's mass, never reach core temperatures high enough for hydrogen fusion. These failed stars, called brown dwarfs, glow dimly from their residual heat and from the fusion of deuterium, a heavy isotope of hydrogen that fuses at lower temperatures than normal hydrogen. Brown dwarfs slowly cool over billions of years, gradually fading from view. The most massive fragments form massive stars, objects with tens of times the Sun's mass. These stars form quickly, sometimes in just a few 100,000 years, and burn brilliantly but briefly. They produce intense ultraviolet radiation that ionizes the surrounding gas, creating glowing H2 regions like the Orion Nebula. The radiation pressure from these massive stars is so strong that it can halt further star formation nearby, blowing away the remaining gas and effectively shutting down the stellar nursery. The wind and radiation from massive young stars create expanding bubbles in the molecular cloud, clearing out regions and compressing gas at the bubble's edges. This compression can trigger new star formation, creating generations of stars, with the oldest stars at the center and progressively younger stars toward the periphery. The entire process is self-propagating until the molecular cloud is either dispersed entirely or exhausted of dense gas. When the most massive stars explode as supernovae after just a few million years, they inject tremendous energy into their surroundings, heating and dispersing the remaining molecular cloud and enriching it with heavy elements created in the star and in the explosion. The shockwave from the supernova can compress nearby clouds, triggering new rounds of star formation. In this way, star formation is a cyclical process. Stars form from clouds, massive stars disrupt clouds, supernova shockwaves compress new clouds, and stars form again. The entire life cycle from molecular cloud to dispersed star cluster takes roughly 10 to 20 million years. The Orion Nebula, one of the most famous star-forming regions visible to the naked eye, contains stars that are only about 1 to 2 million years old, cosmic newborns still surrounded by the glowing remnants of the cloud that birthed them. Over the next few million years, the radiation from these young stars will disperse the remaining gas, leaving behind a star cluster that will gradually spread apart as its members drift through the galaxy. Understanding where baby stars come from means understanding one of the fundamental cycles of the cosmos. The gas from which stars form was once inside previous generations of stars. Those stars fused hydrogen into helium, helium into carbon and oxygen, and heavier elements still, then returned that enriched material to space through stellar winds and supernova explosions. That material mixed into molecular clouds and became incorporated into new stars, including our Sun, which formed about 4.6 billion years ago from a molecular cloud that contained the ashes of earlier stellar generations. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stars that formed, lived, died, and seeded the molecular cloud from which the Sun and Earth eventually emerged, continuing the ancient cycle of stellar birth and death that has shaped the galaxy since stars first began forming over 13 billion years ago.